In this presentation, we are going to see quantum computing and Turing machines. So, the quantum computing and Turing machine, where it covers computational models and quantum versus classical computing. So, we'll also discuss with the future integration of classical and quantum models. So, next, we are going to see the essence of Turing machine. So, I just classify the essence of Turing machine into three types like abstract device, tape information, and basic operations. So we all know that Alan Turing was the scientist who discovered this Turing machine in 1936. So the abstract device is nothing but the Alan Turing conveys a Turing machine. It is an abstract computational device. It's called as abstract device. So next we are going to see the tape operation. So it operates using a tape and which helps to read or write the head, and the tape contains a sequence of symbols which will be helpful for read or write the head. So and the third one is basic operations. So where it includes read, write, and move operations. So it is the basic and foundational for defining the computation, which is our theory of computation (TOC). So and then next we are going to see the key features of a Turing machine. So I just analyzed through Google. So I just read many contents. So in that I take certain key features like infinite tape, deterministic model, and the significance. So the tape offers infinite storage. The Turing machine can operate in one step at a time. So the infinite tape, which offers a infinite amount of storage, so which can operate in one step at one time, and that's called as infinite tape. So and the second one is deterministic model. So it is a deterministic model. However, it faces the halting problem. So they are saying that however, it faces a halting problem. Deterministic model is a deterministic model. So, and the last thing is the significance of the Turing machines. So, it's a significant in classical computation. So, which the machine which it provides model for algorithms. So, this Turing machine is a certain type of model which will be helpful for giving algorithm for a certain type of models. So and next we're gonna see the quantum computing basics. So what are the basic things in the quantum computing? Now we're going to see the basic things of the quantum computing. So from my analysis, I just classify the basic things into three things, basic types into three things. The first one is qubits, and the second one is entanglement, and third one is probabilistics. So the uses of qubits which can exist in multiple states, and the second one is entanglement. Entanglement links states for parallel computation. The entanglement which helps for links the parallel computation states, and the last one is called as the probabilistic, so which it outcome remain probabilistic until measured. So these are the three states. So I mean, the three basic things of quantum computing. The first one is qubits, and the second one is entanglement, and the third one is the probabilistics. The next one is the quantum Turing machine versus the classical Turing machine. So now only the main thing is gonna be start. So I just set the data flow like data flow diagram. So you can see that the first one is a quantum Turing machine QTM, which extends classical machines with superposition, and the second one is simultaneous processing, so which process the multiple paths in simultaneous way. And the third one is classical machine, so which process one computation at one time. So these are the three things. Once again, I'm recalling the quantum Turing machine versus classical Turing machine. The first one is a quantum Turing machine, so which extends classical machine with superposition. With the help of superposition only, the quantum Turing machine extends itself. And the second one is simultaneous processing, where for the simultaneous processing, the process which be held in multiple paths simultaneously. And the third one is classical machine, process one computation at a time. Only one process will be done at a time, so there will not be more number of process. One process will done at a time. And the next thing is computational power of P versus BPQ. So the computational power of P is a complexity class P. So the complexity class P, which will be helpful for solving many number of problems in polynomial time. And BPQ is nothing but bounded quantum polynomial, which will be useful for quantum models. So they are saying that a quantum computer solves specific problems exponentially faster. This advantage makes them promising. So they are saying that the complexity class P and bounded quantum polynomial, these two things which will be helpful for solving the model and solving the problem in a fast and easy manner. And the next thing is we're gonna see the Schwarz algorithm. So this algorithm is a real world implication. So this algorithm is a real world implication. The first one is efficient factoring, and the second one is polynomial runtime, and the third one is cybersecurity impact. So I just classify these three things according to myself. So the first one is efficient factoring, the second one is polynomial runtime, and the third one is cybersecurity impact. So first, what is an efficient factoring? So we get large amount of numbers, so it would be very difficult for us to solve. So on that time we can use source algorithm, so it will be very easy to solve that particular type of the large amount of numbers. So and the second one is polynomial runtime. So what's a polynomial runtime? So as we see in the last slide, so this polynomial runtime, I'm just highlighting it. Polynomial runtime. Yes. So this polynomial runtime, like it will be helpful for solving a large amount of problem. There will be a problem. So it may goes as long as that, like a big problem, So for that type of problems, Shor's algorithm may be used. So it would be helpful for solving those problems, like easy to solve. So and the third one is cybersecurity impact. So the cybersecurity impact, you're gonna say means Shor's algorithm is used in cybersecurity nowadays. So Shor's algorithm are the most significant real world application for cybersecurity, where nowadays, so the past coming years, the past coming days, Shor's algorithm is useful for cybersecurity purposes. So and the next real world implication we're gonna see is Gruber's algorithm. So I categorize Gruber's algorithm in three stages. Like the first one is square root search, and the second one is quadratic speedup, and the third one is applications. So the first one, square root search, is nothing but it enables square root time search in unsorted datasets. And the second one is quadratic speedup. So it offers a quadratic speedup over classical algorithms. It's called as quadratic speedup. And the third one is applications. So as applications in database search and optimization. So we should be this Grover's algorithm is helpful for optimizing the database search. And that's what the Grover's algorithm is saying. So Grover's algorithm is also called a searching algorithm. The next one is visualizing quantum versus classical. So I just categorize this thing into three topics, like qubit entanglement and superposition and complexity comparison. So it's nothing but so first we are going to see qubit entanglement. Diagram illustrates qubit entanglement versus classical states, where qubit entanglement defines that the diagram which illustrates the qubit entanglement versus classical states. And the second one which we are going to see is talk about the superposition. So the representation of superposition in computational pathways. So the superposition is representing in computational pathways, not in a normal pathway. It is representing in a computational pathway. So and the third one which we're going to see is a complexity comparison. So where we in which way we are going to represent the complexity comparison. There will be a question. We are going to represent the complexity comparison in a graphical representation. So it would be the easy and very simple to understand for representing this complexity comparison in graphical method. And the last is the conclusion. So according to my search from the internet, I just got the potential and the challenges behind this Turing machine and its types. So, and what are the complementary role and the future integration.